Okay, so in this video, we are going to introduce our last of the three recursive patterns. Last time we introduced having the input and constant size input patterns, and now we're going to introduce this last one that we call doubling the input. And in this doubling the input pattern, we're going to be examining one problem, which is called the Fibonacci sequence. So don't worry if you haven't heard of the Fibonacci sequence before. It turns out we're not actually going to be doing that anyways. But the Fibonacci sequence is just a sequence of numbers where the next number in the sequence is the sum of the last two. But we are going to be working on what we call Fibonacci-ish, which instead of being the sum of the last two numbers is just the last number added to itself. So I told a bit of a fib there when I said we were doing Fibonacci. So the sequence is easier to describe in code. So the fib function is going to compute this Fibonacci-ish value. It takes an integer n for the number we're trying to compute. If n is less than or equal to 1, it returns 1. Otherwise, it makes two recursive calls. It calls itself, passing it n minus 1. And it's going to do that twice and add those together. So that's what I mean by the next number is the sum of the previous number added to itself. Now, when you think about this recursive call, like when you start with trying to compute fib of 4 is going to call fib of 3 twice, and fib of 3 is going to call fib of 2 twice for each one of those. You can imagine this kind of recursive tree of calls that are happening here. So you start with that fib of 4, and fib of 4 calls fib of 3 twice, and each one of those fib of 3s calls its own fib of 2 twice. What's going to end up happening here is each one of these calls ends up creating two more calls. And those extra calls have almost exactly the same input, but not quite because it's decreased by 1. And so we're going to be calling this almost doubling the input at each call. What we kind of mean by that is when you are thinking about the work done overall, each time you're making one of these recursive calls, you're almost doubling it, not quite. You are doubling the number of recursive calls, but kind of the work overall is almost doubling. So we call this our third pattern, doubling the input or almost. So what we want to do here is we want to figure out what the runtime of this is. We want to find an asymptotic bound. In this case, we're going to try to find its big theta. Since this is a recursive method, I think we're going to just use our regular toolchain to start off with. So let's start with code modeling. And since it's a recursive method, we will use a recurrence. So we start off by counting up how much work is done in the base case. In the base case, we're going to say it takes d steps. Now notice here, for the longest time now, we have been emphasizing that constants don't matter. So when you look at this and you say like, oh, is this 2 operations or is it 3? And we're like, don't worry about it, it doesn't matter. And then you saw the numbers we came up with. You're like, why did you choose those numbers and not one more or one less? Because you didn't trust us that they don't matter. So to really drive this home, we're just on with numbers entirely. We're just going to say it takes d steps in order to do the base case. And we don't care what d is. We just know it's some constant amount of work. Okay, so the base case is going to take constant work. Real quick, I should clarify. I'm going to be saying the word work a lot here. What I mean by work is number of steps. So it takes a constant number of steps. So then when we think about our recursive case, how long does that take to run? How much work does it have to do? Well, we always consider, our non-recursive work. So in this case, the non-recursive work here would be things like doing the addition, doing the return statement. So we'll call that some constant c number of steps. And then the recursive work, well, we make 2 recursive calls, and each one passes in n minus 1. So we need to incur t of n minus 1 steps twice. Now, I want to mention right off the bat here, you saw this plus c, and you already might be thinking, oh, I remember from master theorem we had those constants a, b, and c. Notice I am not meaning to invoke master theorem quite yet. I'm just using some constant here. A, B, C, D are very common names that mathematicians use for constants, and you have to kind of understand from context what we're referring to. So don't confuse this C with the C that we'll use in master theorem. It's just the name for some constant. Okay. So we came up with our recurrence. I wrote it down mathematically. T of n is d if n is less than or equal to 1, or it's 2 times t of n minus 1 plus that other constant work c. Okay, So now I'm going to invoke the master theorem and try to figure out, can we find a bound for this? So if we look at master theorem, you might be able to say here, well, okay, so I need to do this pattern matching that we saw in lecture. So I need to figure out what the constant A is. Oh, well, that looks like a 2, so I'm going to try to write a 2, and I'm writing with my mouse pad, so it's probably not the most beautiful. That's actually a pretty good 2 there. So I figured out that constant A was 2. Okay, pretty good. And now I need to figure out what this constant B is. Oh, wait, this doesn't look like it matches. This is like an n-1, and this is looking for a division. I don't know how to figure out what B is in this context. And so it turns out here that master theorem is not going to work. I kind of mentioned in class on Monday that master theorem is, again, not so humbly named. It's the master theorem. But in reality, it's actually fairly limited. It really only works on recurrences of this exact format. If it deviates at all, like how we're doing subtraction instead of division inside that function argument, it's just not going to apply anymore. So we aren't going to be able to use master theorem here, which kind of sucks because, looking at this recurrence, I don't know what the big theta of it is. I can't just look at that and know. And so this is why we're going to need yet another asymptotic analysis tool to take this recurrence and get us a big theta bound. Before I introduce that tool and the example of us walking through it, I want to try a slightly different approach. I wonder if we can try to see if we could intuit what is going on here, how much work is happening by doing something we call unrolling the recurrence. And what I mean by that is let's actually just write down specific evaluations of this function, starting at 1 and increasing it, and see if there's a pattern on how much work happens as we increase n. So what do I mean by that? Well, let's start by evaluating, well, how much work is done when n is 1? Well, that's our recurrence's base case. So it's just going to be d work. So not too bad. But what if I want to do n is equal to 2? So in that case, that's going to be the recursive case of the recurrence. And so I need to evaluate 2 times t of 1. 2 minus 1 is 1. So I need to call t of 1 plus that constant work c. Well, we already evaluated what t of 1 is here. Well, that's just d. So the whole amount of work done when n is 2 is 2d plus c. Okay. Well, what if I try again with t of 3? Well, with t of 3, I need to evaluate what is t of 3 minus 1. Well, t of 3 minus 1 is t of 2. T of 2 is 2d plus c. And so 2 times 2d plus c. You can do a bit of algebra and you get 4d plus c. And I'm going to kind of speed through the rest of these because it's kind of the same thing over and over again. You get 8d plus 7c, and then 16d plus 15c. And you can probably see that there is a pattern there. Like, it seems to always be of the same form. The numbers are increasing. But it's kind of hard to identify. Like, it's not obvious that, what you could just look at T6 and know what the next thing is. It's kind of maybe hard to describe what the pattern is. And so one thing that helps when you can't always describe a pattern is to maybe try to shift perspectives. Instead of trying to look at this pattern numerically, let's try to look at it with picture, geometrically. So let's go back to that recursive tree, the tree of all the recursive calls that are made. And my argument to you is that in order to find the runtime of this whole of the program, for an input size n, what are the total number of steps? My argument is we just need to figure out how many recursive calls are there in total and add up all the work that's done at each one, right? In some sense, this tree here is the visualization of the whole program running. And if I can figure out how much work is done over the whole program, isn't that the same as figuring out the runtime of the program, right? Assuming, again, saying that work and runtime mean the same thing. So in order to do this, let's try to take this problem apart. Let's start by asking, well, all right, there we go. how many how tall is this tree of function calls? So here, when my picture is starting with fib of 4, it's going to be 4 tall. But in general, it starts with the value n, and then its base case 1. In order to get there, we subtract 1 each time. So I'd argue to you if you had a tree of height n, then the height of that function call tree would be n. You'd have n layers here. N times that you can decrease by 1 before you hit 1. Okay, so that's how tall the tree is. A much trickier question is, well, how many nodes or how many recursive calls are at each layer? So at layer 1, how many recursive calls are there? That's kind of our second question. How wide is the tree at each point? And you can see kind of a pattern here, where at the first level there's 1, and then it doubles to 2, and then that doubles to 4, and then that doubles to 8. Whenever you see this doubling each time, you should start thinking of powers of 2. So the powers of 2 are a very common pattern in computer science applications. And so whenever you see this doubling nature, you should be thinking of powers of 2 as your pattern. So at layer 0, there is 1 function call. At layer 1, there are 2 function calls. At layer 2, there's 4, 3, there's 8, doubling each time. We can more concisely write that as 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3, respectively. And again, just for notational convenience, we're going to call that first layer, the one at the top, layer 0, just for simplicity. So that means the number of function calls on layer I is going to be 2 to the I, right? You can see that pattern in that table here. So if I want to figure out the total number of function calls across, say, k layers, you can also put n in there if you want to figure out the whole tree, but just in k layers, well, that's going to be 1 plus 2 plus 4 plus ... all the way to the k minus 1. Why do I stop before k? Well, it's because we include 0 as our starting point. So in k layers, index layer 0 is included there, just like, and so we can't include 2 to the k. Kind of like when I'm talking about k as being 4, a tree of height 4, we stop counting at 2 to the 3, 8 things. So we stop 1 early in some sense. Okay, so that's a little tricky to wrap our head around in this simple case of just 4 things. But what if I want to talk about more generally, like if I had a tree of height n, and I want to talk about the whole method call? So to do this, we need to solve this in parts. And we'll actually see a kind of slide like this multiple times, where I have a series of questions to help you walk through how to tackle these problems. So let's start by asking, how many layers are going to be in the function call tree? Well, in this context, it'll be n. If we're talking about a tree, if we're talking about trying to figure out the runtime for fib of n, well, this tree is going to be n tall. How many function calls will be on layer I? Well, we kind of answered that on the last slide. It'll be 2 to the I. And so the total number of function calls across all n layers would be 1 plus 2 plus 4 plus 8. That's the sum of the number of function calls in each layer. And we do that all the way up to 2 to the n minus 1. Again, stopping 1 early because we're including that 0 indexed layer. Okay, so that's the total number of function calls that happen totally. And now our argument is that the total runtime is going to be the total number of function calls times the runtime of each of those function calls. Now, importantly, one thing I should highlight is in this analysis, we're going to assume that every function call takes constant time. And that's going to be true in our case, right? In the base cases, we said it was d steps. And in the in the recursive cases, well, that non-recursive work, the stuff we were doing outside the recursion, was also constant. And so this analysis will be a bit simpler than what we're going to see later, where we can't make that assumption. So here, the total runtime is going to be the total number of function calls times the runtime of each function. So we have 1 plus 2 plus 4 plus 8 plus ... plus 2 to the n minus 1 times some constant work. Now, I'll already start by saying it's pretty tedious to have to write out 1 plus 2 plus 4 plus 8 plus ... plus 2 to the n minus 1. Trust me, I did this in PowerPoint. It's not fun to write things in PowerPoint. So first, I want to introduce some notational convenience to talk about these sums. So we're going to use this summation notation, this sigma in Greek, uppercase sigma. Really, this notation looks weird the first time you see it, but it's actually really straightforward if you know programming. It's really just a for loop encoding a sum. So when you see this sigma, the bottom thing tells you what are you starting at. We're starting at I equals 0. The top thing tells you where you stop. We're stopping at n minus 1. And then because we're using a big sigma, S stands for sum, we're going to be summing up all the values inside, starting at I equals 0, going to n minus 1. And what are we adding up inside? 2 to the I. Notice what I did here is I said each layer, I, there are 2 to the I recursive calls. And so I'm just adding that up. 1 plus 2 plus 4 plus 8 plus 2 to the n minus 1. We're just writing this down in a very compact and concise notation. Now, one of the things I do want you to be able to do is be able to write these summation notations down and be able to read them. So we do want you to be comfortable using these summations like notation to describe sums. What I'm going to show you next is kind of a trick, pretty cool trick, but not one that we're just going to take for granted. So it's cool and all that I can write the sum of numbers down, but it's still kind of verbose and also doesn't tell me, okay, well, if n is 200, what is this sum? Do I actually have to write a program to compute what that sum is? And it turns out that mathematicians have thought about summations for a long time, and they've come up with a bunch of what we call summation identities. What we mean by that is they've proven to us that this sum is equal to this value under some context. So when we see the sum of the powers of 2, what's going to call to mind is this thing called the finite geometric series. And again, these identities we're just going to take as fact. We are not going to prove that this thing is equal to this other thing. We're going to take these for granted. And on the website for today, we have a cheat sheet of all of the summation identities that we want you to be able to use, but we are not going to prove that any of them are correct. We're just going to take them for granted. So what this summation, this finite geometric series identity says is if you have the sum from I equals 0 to k minus 1 of some value x to the I, well, we already just know what that value is going to be. It's going to be equal to x to the k, value quantity minus 1, divided by x minus 1. So mathematicians have shown that when we have this series of sequence of powers of 2, when we're adding them all up, we just know what the answer is. We have a closed form. Closed form normally just means something without like something you have to solve for. So you don't have to take any more sums. You just can compute what the answer is. So plugging in our values here into this finite geometric series, what we're going to do here is we're going to say, well, our value of k here, k minus 1, we're using n minus 1. We're using 2 as our x. And so our final formula here is going to be 2 to the n minus 1 divided by 2 minus 1, just plugging in that formula right there. And simplifying that, that ends up becoming 2 to the n minus 1. Because 2 minus 1 is 1. So we're just dividing that by 1. So that whole sum, the sum of 1 plus 2 plus 4 plus 8 plus dot 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 plus 2 to the n minus 1 is actually equal to 2 to the n, 1 less than that. Which is really, really cool. Very useful powers of 2 fact. But this finite geometric series actually is more general than just powers of 2. It works for lots of other powers. So we have now a closed form for how many function calls there are. For an input n, there are going to be 2 to the n minus 1 function calls in total, if you sum up all the layers. Now, one of the things we're going to do right now is we're actually just going to get rid of this constant work. The reason I'm going to get rid of this constant work is we're about to do an asymptotic analysis on this, and we're going to drop the constant anyways. So our runtime is now going to be something like 2 to the n minus 1, which is going to be big theta of 2 to the n. Okay, let's take a pause there. What did we just do? We just calculated the number of recursive calls that happen in total. And we said, okay, well, since each one is going to have a constant amount of work, we just drop the actual constants. In total, for a tree of height n, there are going to be 2 to the n minus 1 recursive calls totally. And so then, now that we have this formula, we can now just use our regular asymptotic analysis, because notice this formula is simple in the sense that it's not a recurrence, it's not a summation. It's just a function. And so we can just drop this constant minus 1 and say, oh, this is big theta of 2 to the n. So lots of things we just did there. What I want us to do is I want us to do a bit of recap of kind of where we've been this whole past 2 lectures. So what I've done here is I've put our three recursive patterns, having the input with binary search, constant size input with merge sort, and doubling the input with Fibonacci. And through our analysis, the first two using master theorem, we found that binary search was big theta of log n. We found that merge sort was big theta of n log n. And now with this new tool, which I haven't formally described yet, which will be a bit more generic, we're going to call the tree method, I've shown you that Fibonacci is big theta of 2 to the n. And so what I've done above is I've actually plotted these functions. So when you're looking at small n, log n, log n, and 2 to the n, they actually look relatively similar. I mean, you can kind of already see that last one, 2 to the n, is starting to increase faster. But really, to get a sense of scale, 1 to 5 doesn't quite cut it. You really have to start looking at bigger n. So with bigger n, you can see that that 2 to the n grows very, very quickly. Much, much quicker than log n or n log n. They actually look the same in that right graph. Now, don't get me wrong, log n and n log n are definitely different runtimes. Log n is much preferable in some sense. It's a factor of n better. But 2 to the n grows so quickly, it makes everything else look very efficient in comparison. Like, look at that. In this graph, we're only going up to n is equal to 10. And we're already at like 1,000 steps there for 2 to the n. If you increase that input by 1, it's going to double again to over 2,000. Every time you increase that input size by 1, it doubles the runtime. And so even for moderate sizes of n, it will take longer than the age of the planet to actually compute. So hopefully this gives you a sense of scale of what this Fibonacci is computing. This doubling the input actually can happen in real life applications. And they can be kind of scary in the sense that even for moderate input sizes, you're not gonna be able to actually compute anything useful. Now, in the next video, what I'm going to introduce is a more general thing of a process of what we just did. A lot of what we just did was very specific to this Fibonacci sequence with a lot of constant work that we forgot. We're going to call this the tree method. And with this tree method, we'll be able to handle basically any type of recursive code here. Okay, so with that, I'll stop this video and I'll see you in the next one.